We're now going to talk about the convergence of the proximal point algorithm. In fact, we've already established the convergence of the proximal point algorithm when we were talking about the proximal gradient, and we'll make that connection explicit in a second. Also, in this lecture, I want to make the connection to a bit deeper theory on fixed point operators and convergence there, and give you a few of the basic definitions. And these are going to be useful for us later on when we talk about other splitting methods. Okay, so our proximal point algorithm, again, minimizing a function f that's convex. My proximal point algorithm is xt plus 1 is prox lambda f of xt. We've already seen that this converges. This has 1 over t convergence rate if you're using a fixed step size lambda. So how do we see that? What did we do when we did all our work on proximal gradient? For proximal gradient, where did we apply this? We applied this to the setting where f of x is equal to g of x, which is smooth, plus h of x, which is proximable, which means that it has an easy to evaluate prox operator, ideally, because we don't need that to define the algorithm. But that's exactly what we have in this case. So here we indeed have that, because f of x is equal to 0, which is smooth, plus f of x. You see, this is a very deep equation here that I've written. And if I apply proximal gradient to this, what does it look like? Proximal gradient to the setting is telling me that xt plus 1 is equal to the prox function of f evaluated at a gradient step with respect to the first function, which is 0. So indeed, I mean, I'll just write this out. This is xt minus eta times the gradient of the 0 function, so that goes away. So indeed, this is just the proximal point algorithm is proximal gradient. So we can just repeat our work from before, and we know that this converges. Then you might recall a little bit more carefully, though, that when we were talking about proximal gradient, we were restricted to take a particular step size, because the step size was governed by beta, the smoothness parameter of g, as I've written it here. Whereas in this setting, g is the 0 function, and the 0 function is smooth for any beta, arbitrarily small. Remember, our step size was 1 over beta. So now essentially this is saying that you can take a step size as large as you want. So you can have extremely fast convergence. And of course, this makes complete sense. So let's remember what prox is. So just writing this down, prox is the argmin of f of x plus 1 over 2 lambda times x minus xt. And if I'm taking a very, very, very large lambda, a very large step size, that just exactly corresponds to minimizing f of x. So first of all, the question is, we have to be a little bit careful. We're trying to make a specific statement about convergence, and indeed, we immediately get back our 1 over t convergence. In terms of complexity and how useful and where this is useful, we just have to keep in mind that sometimes having a very small lambda should typically mean that we have a harder problem to optimize. In particular, we've seen that when lambda is very small, which means that you care very much about the proximal term, then this proximal point algorithm is essentially as easy as gradient descent, because it is gradient descent for very small lambda. Again, this just intuitively makes sense looking at the definition of the proximal point algorithm. So if lambda is very small, the quadratic term is huge, which means you have to stay very local. Very local, you have a linear approximation, and that's exactly where gradient descent comes from. Okay, but it's worth seeing this a little bit more in detail and also refreshing our memory a little bit about the proximal point algorithm. So let's actually prove this. Let's go back and fill in some of the details here about the convergence rate. So what had we defined back then? So remember that we had defined the following. We had written a little bit more carefully. If xt plus 1 is equal to the prox of lambda h, I'll write it in that same notation of when we have f of x is equal to g of x plus h of x, evaluated at a gradient step with respect to g, xt minus eta times the gradient of g of xt. And in order to perform our analysis, we had really wanted to mirror the proof that we had for smoothness. And so this motivated us to define the gradient mapping. And in order to define the gradient mapping, we wanted to write xt plus 1 is equal to xt minus lambda times something. And we called this g. This is called we call this the gradient mapping. We use this for projected gradient descent. We use this for the more general setting of proximal gradient descent. And just using this equation here, the equality of the last two lines, you find that g of lambda, again, this is purely just solving it, g lambda of x is equal to 1 over lambda times xt minus prox. Whoops, sorry, that should be, I skipped a little step. I went back to our definition here, so let me rewrite that. Where g lambda of xt is equal to 1 over lambda times xt minus prox lambda h of the gradient step. Xt minus eta gradient g of xt. But for our setting, where we're setting f of x is equal to h and g is equal to 0, what this reduces to is simply g lambda of x is equal to 1 over lambda xt minus prox of f evaluated at xt. So we have this. Now, looking back at the work that we had done then, we can use, we obtain that f of xt plus 1 minus f of x star is upper bounded by g lambda of xt minus x star minus lambda over 2 times the norm of g lambda of xt. This is the consequence of the inequality we had worked so hard to show, which basically replicates that key inequality that we have when we're just minimizing a beta smooth function. By completing the square, this is just equal to 1 over 2 lambda of xt minus x star squared minus xt minus x star minus lambda times g lambda of xt squared. So you can see what happened here. Xt minus x star is going to go away because that's present in both terms, and I'll be left with just the cross term and then the g lambda squared square term. But this here is exactly xt plus 1. So here is my telescoping sum, xt minus x star squared minus xt plus 1 minus x star squared. Again, 2 norm. I'm just being lazy here. And what this tells us is multiplying through by lambda, or even more generally, a step size lambda t at time step t. This tells us that lambda t of f of xt plus 1 minus f of x star is bounded by 1/2 times this telescoping quantity. And if you sum this up, take the telescoping sum, I'll leave this for you to finish, the details are straightforward. You can conclude, so I'll just write sum to conclude that f of xt minus f of x star, the suboptimality, is upper bounded by x0 minus x star squared divided by twice times the sum of the step sizes that you take. So if you take a fixed step size or a step size that's bounded away from 0, then you're going to get 1/t convergence. And so a little bit more carefully, and it also reminds us of what we had done. Now we can also apply ideas from acceleration. So we can use a FISTA like acceleration algorithm. So basically, just taken verbatim from accelerated gradient Prox, proximal gradient, our algorithm is we initialize somewhere. x1 is equal to a proximal step of x0. And then subsequently, our iteration is going to, again, have this flavor of acceleration, which is momentum. The key aspect is momentum. xt plus 1 is equal to prox lambda tf of xt plus a parameter theta t, which I'll define in a minute, 1/theta t minus 1 times xt minus 1. This is our momentum term. And how do we pick these? So we see we have lambda t's and theta t's. So we choose any sequence, lambda t, and then the theta t that solves an equation that's fully specified once you've specified the sequence of lambdas. Theta t squared divided by lambda t equals 1 minus theta t times theta t minus 1 squared over lambda t minus 1. And you can choose any sequence lambda t's you want, and convergence is guaranteed if you have sum of square root of lambda t going to infinity. And certainly this is satisfied for a fixed schedule, lambda t equals lambda for all t, and for that fixed schedule we get back the accelerated convergence rates that we expect, which is basically 1 over t squared. So this is really just saying we've already done a bunch of the work for to get convergence. But I also want to use this as an opportunity now to talk a bit more generally about convergence the link to a little bit of a deeper theory of convergence of different operators. So to make this link, let's again write. We know that for f, our convex function that we want to minimize, this Prox operator is a mapping from Rn to Rn, and it's a mapping such that what is its key property? Its fixed point property is basically saying that a fixed point of this Prox operator is a solution to our problem. This is relatively simple, but it's worth stating because it's basically the point of departure for a much more general theory of how you can think about designing iterative algorithms and trying to prove their convergence for a number of different problems. So this property is that x hat is a fixed point of the Prox operator exactly if and only if it solves the original problem. And another way for us to write that is that 0 is an element of the subdifferential of f at that point x hat. So in other words, if and only if x hat is an optimal solution. Doesn't have to be unique. And to see this is basically just as trivial. We just need to write it down. But we might as well do that. So if x hat is a fixed point, that means that x hat is equal to prox lambda f of x hat. Let's write down the definition of prox. And so this means this is equivalent to writing that x hat is an element of the argmin of f of x plus 1 over 2 lambda times x minus x hat. And then writing down the conditions here, this is equivalent to writing that 0 is an element of subdifferential of f at x hat, plus now we just take the derivative of this other part, the 2 comes down, I get 1 over lambda times x hat minus x hat, 0, which is exactly saying that, that x star is an optimal solution. Okay, simple point, Prox operator is a mapping from Rn to Rn, and fixed points of the Prox operator are the solutions to the original problem that we care about. So let's think about this more generally then. So now I'm going to let T be an operator from Rn to Rn. It could be single valued or multiple valued. So single or possibly multiple valued. Example of single valued, Prox. Example of multiple valued is the subdifferential. And let's define fixed T to be the subset of Rn that is a fixed point. And I'm going to assume throughout, even if I don't write it, that this is non-empty. The same way that we just assume that our optimization problem has a solution, so we don't have to deal with that particular additional complexity. So the central question of this general theory is, what do we need to have about T in order to guarantee that it converges? Because it is very easy for any problem in the world to write down an operator whose fixed point is what you want. You could just, in a way, just make it so. The operator that just outputs the right solution, for example, if you it's a fixed point, but what does it do? What does it do outside of that? So the question is, when does the iteration or the iterative algorithm xt plus 1 equal to t of xt converge to a fixed point? One simple answer is if t is contractive. So one possible answer is if t is contractive, or in other words, if t is a contraction mapping, this means that tx minus ty is less than L times x minus y for some L that's strictly less than 1. So I'll leave this as an exercise for you to show, namely that in this case t of xt, this iteration, converges to some fixed point in fixed t, and also you can show that there has to be a unique point. So show this, and then I also want you to show, just to make sure that the connection is clear to everything else that this class has been about. Also prove that the operator that's equal to identity minus lambda times the gradient of f, not the Prox operator, this is also namely just gradient descent, is a contraction when f is beta smooth, alpha strongly convex, and when we have a proper choice of lambda. So try these out. But then now you'll immediately realize that actually most of the things that many of the things that we've been talking about may not enjoy this contraction property, and in fact may just have L equals 1. So when we have property star with lambda equals 1, this is called non-expansive. It's saying that tx minus ty is not going to be farther, it's not going to be more than x minus y. T is called not contractive, but called non-expansive. And the question is this enough? Is this enough to guarantee convergence? And the answer, of course, is no. It's easy to see that. Multiplication by minus 1 is an example of a non-expansive operator. Rotation is an example of a non-expansive operator. So by itself, this isn't enough. So we need to define an additional property that's going to give us convergence in this setting of non-expansive. Well, a non-expansive operator is called alpha averaged if T is an average of a non-expansive operator and the identity. And we'll see through a picture why this is critical. I is the identity, plus alpha times some t prime for some non-expansive operator t prime. And a simple lemma is that T is alpha averaged. This is equivalent to writing that Tx minus Ty squared is less than or equal to x minus y squared. Okay, by itself, this is non-expansive. But it's slightly better than non-expansive without being contractive. Minus 1 minus alpha over alpha times Rx minus Ry, where R is defined as the residual, where R equals I minus T is the residual mapping. When is R 0? R of x is 0 when Ix equals Tx. In other words, when we're at a fixed point. So R is non-zero unless you're at a fixed point. So what this inequality is saying is that you are not going to be always better than just a simple non-expansive map, but you are going to be better as long as you're not at a fixed point. And the farther you are from a fixed point, the better, the more your improvement is going to be. So in other words, the intuition is that we improve the basic inequality of non-expansiveness by the amount that's proportional to fixed point violation. So let me write that down. The intuition is that we is that we improve the inequality by an amount that's proportional to fixed point violation. This is the idea. Another piece of jargon that you'll see everywhere if you start reading about fixed point operators is that an alpha averaged operator for alpha equals 1/2 is called firmly non-expansive. Main point, if we have an alpha averaged operator, alpha is less than 1. If alpha is equal to 1, then just let's flip back for a second to see. If alpha is equal to 1, then all we have is non-expansiveness. Because if alpha is equal to 1, then this term here goes away. So if we have an alpha averaged operator for alpha less than 1, then the iterates converge to a fixed point. This is the main result, which is actually pretty straightforward to demonstrate. If T is alpha averaged for alpha less than 1, and again, fixed points of T are not empty. And we look at the and the iteration we're studying is xt plus 1 is equal to t of xt, then we know a few things just from the property of alpha averaged that's promised by the previous lemma. That just takes a little bit of algebra to show from the definition of alpha average to the lemma. So that's but using that, this, even though this is the main result, it's fairly immediate to show. Xt plus 1 minus any fixed point x star is decreasing. So this is monotonically decreasing. We don't have to have a unique fixed point for this to be true. In particular, though, this may not go to 0 because of that reason. Also, you can show that xt plus 1 minus x star squared is less than or equal to x0 minus x star squared minus 1 minus alpha over alpha times the sum from tau equals 1 to t of the residual r x tau squared. Let me give you the intuition in pictures because I think then it's almost immediate. So what is an example of an operator that is non-expansive but doesn't converge? One maybe canonical example you can think of is rotation. So let's imagine that t is averaged. What does that mean? T is equal to 1 minus alpha times the identity plus t prime, where t prime is non-expansive with no further guarantees. So let's take t prime to be rotation and see why iterating t, not t prime, is going to converge. Again, proof by picture is nice, I think. So here's your original point xt. Here is it rotates. Here is your point t prime of xt. But t of xt is going to be some average. And so you see what's happening when we're talking about the 2 norm. I'll just write the halfway point, but alpha doesn't have to be half unless it's firmly non-expansive. But just to draw a point, I'll draw it somewhere. So this is the point t of xt. And so basically what the picture illustrates is that I just got closer to the fixed point. The fixed point of t and t prime, they're actually the same. The only fixed point, and indeed you can check this, that whenever you have an operator t that has a fixed point, sorry, t prime that has fixed points, if you look at the alpha averaged version of it, that is going to have the same fixed points. So actually that tells us something important, which is that if we have an operator that has the fixed points we want, even if that operator doesn't necessarily converge if we iterate it, what we know is going to converge is if we just dampen that operator, because this averaging is exactly a dampening property. So an immediate consequence, I guess, one note here is that t prime and t have the same fixed points. So that's straightforward but important. Then a consequence of this is that if t is your fixed point operator, in other words, when I say your fixed point operator, I mean the operator that has the fixed points that solve the problem that you care about. So if t is your fixed point operator and it's non-expansive, but we don't know anything about convergence, then if you look at the algorithm, xt plus 1 is equal to 1 minus lambda t times xt plus lambda t times t of xt. You see, I'm exactly just looking at an average between the identity mapping and t. Then the sequence that you generate is going to converge to a fixed point of t. This is what we're saying here. I want to wrap this up with just a few more properties of averaged operators and fixed points. The first important thing is compositions. If ti is non-expansive, and these are relatively straightforward to check, then t, which is just the composition of these operators, is also non-expansive. And if ti, for each I, if it's non-expansive, and at least one is contractive, then t is contractive. Again, t defined just as above. And alpha averaged has a similar property, except they all have to be alpha averaged, which you'll be able to see from this definition. If ti is alpha I averaged, then t is also averaged, but the alpha is k, this is the number that you're averaging, over k minus 1 plus 1 over max alpha I. It's this averaged. So in particular, you'll see that if even one of the t, if I have a bunch of alpha averaged operators, and one of them is alpha averaged with alpha equals 1, which means it's just non-expansive and nothing more, then I don't have a guarantee without any additional information about their composition. So let me close this lecture by giving you a few familiar examples and leaving you with some exercises. So first, if f is convex and smooth. Now in a previous slide I asked you to show that if f is strongly convex and smooth, then t is contractive. But now I'm just saying convex and smooth. Then t is equal to identity minus lambda gradient of f. Again, this is just the gradient descent operator. Then this is an averaged operator. Again, for the right choice of lambda. So show this. And the other example, which is what we've been working with, is for t equal to a backwards operator that is now very familiar to us, inverse. So again, this is our proximal point algorithm. Then in fact t is alpha averaged for alpha equals 1/2, which, remember, this means that t is firmly non-expansive. These two facts, combined with the previous slide's conclusion that I wrote at the bottom, that the composition of alpha averaged operators is alpha averaged, with the conclusion of the slide previous to that, which says that iterating alpha averaged operators converge to a fixed point, basically tell us that, so combining A, B, and previous slides tell us that if I look at the operator, that is the composition of I plus lambda delta H inverse composed with I minus lambda gradient of G is an averaged operator, and hence it converges. And what is it? What is this operator? This is exactly our proximal gradient operator. First, we take a step from xt to xt minus lambda gradient of g of xt plus 1, and then we take a prox step with respect to h. And so we worked to show specifically that that operator converges using properties of smoothness and convex functions, etc. But if you use those properties to just establish that your functions are alpha, your operators are alpha averaged, this combination, along with the fact that composition of alpha averaged operators is alpha averaged, tells us that prox grad converges. We're going to pick this up next time and talk more about properties of convergence and proximal point in the dual and in the primal.